This presentation aims to outline Avogadro's constant and how to use it in calculations. Let's first consider this idea of the mole. The mole in chemistry is similar to the idea of a dozen. So a dozen means 12, 2 dozen means 24, half a dozen means 6, and so on. So we give the term dozen to mean a fixed number. And the term mole is used in the same way in chemistry. It's a fixed number. It's a big number, but it's a fixed number. Let's just do a quick calculation. I've got 36 eggs. How many dozen eggs do I have? So I would imagine that you would have leapt to the conclusion that we've got 3 dozen eggs, and that's the correct answer. So 3 dozen eggs. But actually, subliminally, what you did was the following calculation. You decided that the number of moles, or the number of dozens in this case, equals to the number of eggs that I have, divide through by the number in every dozen, which in this example was 36 divided by 12, which is 3. So in chemistry, the mole then is just a number of things. That could be any old things. It could be people, it could be eggs, it could be bread buns, it could be molecules, atoms, electrons, and so on. It just means a number of something. It's a pretty big number. It's this number here, 6.022 times by 10 to the power of 23 if we call that to 4 significant figures. And this is called the Avogadro constant, or Avogadro's number. It's sometimes given the abbreviation NA, like so, Avogadro's number. Actually, it wasn't determined by Avogadro, this guy in the picture here, but it was named in his honour, and I've asked you to do a little bit of reading about that as part of this week's work. Before we continue on this story, why on earth does the mole matter? Well, the mole matters because it's a bit like a translator. It's a bit like a translation dictionary. We've got 2 key languages in chemistry. We've got the language, if you like, of formulae and equations. And those things deal with numbers of and ratios of. But the problem is that the types of substances we are trying to work with, atoms, molecules, are so small that we cannot just count out individuals of or specific numbers of. What we need to be able to do is convert into the language of measurements in the lab. And those measurements in the lab might include things like volumes, they might include things like masses, densities, etc. So this really allows us to translate between those 2 languages to be able to know how many of something we have, but by doing that in a measurable way in the lab. Okay, back to Avogadro's constant. Let's have a look at this then. So Avogadro's number is given at the top of this slide. Imagine that we've got a sample containing 2.4088 multiplied by 10 to the power of 24 argon atoms. How many moles of argon atoms do we have? So in order to work this out, what we need to do is a similar calculation to what we did with the bread buns or the eggs earlier. We're going to say that the number of moles equals the number of particles that we have, in this case argon atoms, divided by the number of particles in 1 mole. And of course that's Avogadro's number. So this would be the 2.4088 times 10 to the power of 24. Divide that through by the 6.022 times 10 to the power of 23. And what you should get is 4.000 moles. Notice that I've stuck with 4 significant figures here. This value was given to 4 significant figures. This one was given to 5 significant figures, but we have to stick with the lowest significant figures that we've got. So it's good practice to do that through the calculation and in the answer like so. Let's have another example then. Here's a sample containing 0.0150 moles of water. This time there's 2 questions. First of all, calculate the number of molecules, and secondly, calculate the number of hydrogen atoms. So let's consider this H2O, this water that we've got. So we know that we've got the number of moles available there, but I'd like to know the number of particles that we have. So using the idea that number of particles that we have is equal to the number of moles that we have times by the number of particles in each mole, as in Avogadro's number. So in this example, the number of particles is the number of H2O molecules. That's the moles, so that's 0.0150 times by Avogadro's constant, 6.022 times 10 to the power of 23. Let's put that in a calculator, 0.0150 times by 6.022 times 10 to the power of 23. And that should give 9.03 times 10 to the power of 21 molecules. Now pause for a moment and see if this makes sense. I've used 3 sig figs this time because this one was to 3 sig figs, which was the lowest number of significant figures, so that bit makes sense. This is a smaller number than Avogadro's number, so less than 1 mole, that also makes sense. And it's smaller by a couple of orders of magnitude really, which makes sense here because this is smaller than 1 mole by a couple of orders of magnitude, so that's looking sensible. Now the second part of this is calculate the number of hydrogen atoms. Now in order to do this, we need to use the formula of H2O and the principle that every 1 molecule of H2O contains 2 hydrogens and 1 oxygen. So for every 1 molecule of that H2O, there are 2 hydrogens, so 2H per molecule. So this is now just using ratios. So the number of hydrogen atoms here is equal to 2 lots of the number of molecules. 2 times by 9.03 times 10 to the power of 21 equals 1.81 times 10 to the power of 22, again to 3 significant figures. So we've got double the number of hydrogen atoms as we had molecules of water, which makes sense because every water molecule contains 2 hydrogen atoms. Let's take these calculations just one step further then. So in the final example on the handout here, on the video should I say here, we've got a sample this time, it says, containing 44.0 milligrams of carbon dioxide, so CO2 here. And it's asking us to calculate the number of molecules of carbon dioxide. Well, if I know the number of moles of carbon dioxide, I can easily calculate the number of molecules. But at the moment, I don't know the number of moles. So this is where you're going to have to go back to some other ideas that you've used before. So in this example, the number of moles is equal to the mass in grams divided by the MR of CO2. The mass that we've been given is 44.0 grams. Now at A level, it's important to use the MR values from the periodic table. And the MR values from the periodic table are given to 1 decimal place each. So CO2 has MR equal to 12.0 for the carbon plus 2 lots of 16.0 for the oxygen. So the MR needs to be quoted not as just 44 here, but 44.0. So 44.0 milligrams divided by 44.0. Now, of course, this only works if that mass is given in grams. So if this is milligrams, that's 44 times 10 to the power of minus 3 grams. let's have a look at what that comes out as then. 44 times 10 to the power of minus 3, all divided 3 by 44.0 equals 1.00 times 10 to the power of minus 3 moles of CO2. Now that we know the moles, we can say that the number of CO2 molecules, that's now easy. It's 1.00 times 10 to the minus 3 moles times 3 by the number of molecules in 1 mole, so that's 6.022 times 10 to the power of 23, and that should give us a total of 6.02 times 10 to the power of 20 molecules in that sample, that being to 3 significant figures, 3SF, because this value here was 3 sig figs and this value here was also 3 sig fig, so that limits 3 sig figs in the answer. Okay, by now you should be able to understand what Avogadro's number means and to use it in a variety of calculations, so it's time to go and have a bit of a practice.